thank you very much for the introduction. And as Dr. Murphy said, I'll be talking about the effect of ionizable lipids in simplified systems. But why are we talking about ionizable lipids? That's because they are in newly developed lipid nanoparticles. So lipid nanoparticles have been used for small molecule drug delivery for quite a while, but there is currently an expanding field of research looking at the use of lipid nanoparticles for the delivery of genetic material, such as DNA or RNA. And although this was initially focused on genetic disorders, it's now expanded to address a much wider range of diseases, including COVID more recently. So we need to use a delivery vehicle for the genetic material for a few reasons, including limiting immune response to RNA and also increasing the stability of the genetic material so that it arrives in one piece where it's supposed to. And one of the more recent developments in the field is the use of cationic ionizable lipids. So what are they? These are lipids which have a charge dependent on their environment. And this property allows them to address some of the challenges that are currently associated with lipid nanoparticles. One of them is efficient encapsulation of the RNA, so it more efficiently kind of binds to the DNA or RNA during the self-assembly of the lipid nanoparticle. And then also helping to release the RNA and DNA into the cell when it arrives there. So we are interested in studying the behavior of these cationic ionizable lipids as they're fairly new. But in pharmaceutically relevant lipid nanoparticles, they're very complex, they're multi-component systems, and it's very hard to isolate the individual contribution for one lipid. So we are looking in a simplified system. And the lipid we're specifically looking at is D-lin MC3-DMA, which is an ionizable lipid positive at low pH with an apparent pK of approximately 6.4. As MC3 is not a bilayer forming lipid, and we would like to look at a supported bilayer, we use DOPC as a helper lipid, and we vary the ratio of MC3 to DOPC, so looking at 0, 5, 10, and 15% MC3 in order to look at its effect on the structure of the layer, and then also look at its interaction with mRNA. Or because mRNA is expensive, an mRNA model we mostly use is polyadenylenic acid, or poly-A. And then for some of the experiments, we did use EPO-mRNA. And because it's an ionizable lipid, we are looking over a cell-relevant pH range of pH 6 to 8. So as the previous speaker very helpfully introduced, I also did some QCMD. And I'll just show a few of the measurements to highlight some common features and key points, and then summarize them. So this is the QCMD experiment we did for the 15% MC3, so that's the highest proportion of MC3 in the layer, and pH 6, which is below the pKa of MC3, so it should be positively charged. So what we can see from the bilayer deposition is we get fairly typical frequency and dissipation shifts expected for a bilayer. And then after flowing over with a buffer to set the pH, we then flow through poly-A. And you can see in the graph here, we see a sharp decrease in frequency and a sharp increase in dissipation, indicating that mass has absorbed to the surface and that the layer has become less rigid, which remains after rinsing with buffer, indicating that poly-A is irreversibly absorbed to the surface. So we see this for 10% and 15% MC3 in pH 6. However, we don't see any absorption for 0 and 5% MC3 at this pH. Then looking again at the same composition of the layer, so 15% MC3, but a slightly higher pH above the pKa, we see similar values for the deposition of the layer. However, when we then flow through poly A, although we see an initial decrease in frequency and increase in dissipation, when the sample is left to equilibrate and then rinsed with buffer, there is a return to pre-poly A values, indicating that there is no absorption. And we see this also for the other pHs above pKa, pH 7 and pH 8. So to summarize, the poly A absorption in the QCMD, we do see a similar adsorbed mass for all of the compositions in all pHs. And for the poly A, for all of the pHs above the apparent pKa, so 6.5, 7, and 8, there's no significant absorption of the poly A. However, for pH 6, so below the apparent pKa, we see a poly A absorption proportional with the percentage of MC3 in the layer. So then to look at the dynamics of the layer a bit more, we did some total internal reflection fluorescence microscopy. And we used a fluorescent probe in the layer, very dilute, pH independent probe to look at dynamic behavior. So when imaging the lipid layer in, this is the 5%, in all of the pHs, we can see a homogeneous fluid layer shown in the pictures. They all look pretty similar. Then we also did some fluorescence recovery after photo bleaching, so FRAP, where we photo bleach a section of the layer there and then watch for the fluorescent recovery. And we see full recovery after 30 seconds. This is for pH 6.5, indicating that this could also, or also supporting that this could be a bilayer structure. From the FRAP, we can calculate the diffusion constant and immobile fraction of the probe. And as they're shown in the table, you can see within experimental error, they're not significantly different. Although these values are higher than typically reported in the literature for DOPC layers alone, indicating that the MC3 could have an effect on the layer such it's not a simple bilayer structure, and there could be something else affecting the mobility of the probe. So after looking at the layer alone, we then incubated with poly A, rinsed with buffer and remeasured. And there weren't any significant changes to any of these values. And this also was the case for the other compositions, for the other pHs as well.
Yes, go.
Thank you. So then we also did some reflectometry measurements where we measured the same lipid compositions, but only pH 6 and pH 7, and this time with mRNA. And what was interesting this time is we saw after addition of mRNA to the lipid layers, we saw changes for both pH 6 and pH 7 for 15% MC3, but only in pH 6 for 10% MC3, and not for any of the others. So I was hoping to show you the fitting, but we're currently working on that with some partners who are doing MD simulations, where we do see some very interesting behavior from the MC3. So comparing different force fields in the MC3, for the MC3, we see that there are three force fields currently that have been put out in publication, and they agree very well for the protonated MC3, where we have a more bilayer-like behavior, but for neutral MC3, we have very different behavior for the models, which we're hoping to investigate further with this fitting. So then, just to quickly conclude, the absorption of poly A and mRNA both depends on the pH of the system and the proportion of MC3 in the layer, although to different extents. We have a rather unusual structure of the layer, although some, the QCMD and some of the TERF results indicate a bilayer-like structure. From the neutron reflectometry and simulations, we see much more variety and a difference depending on pH. And with that, I would like to thank everyone who helped with the work and contributed, especially Tommy and my supervisor Tommy, and Marco Financier, who helped with who did the turf measurements. And thank you very much for your attention.